Okay, so you just got to see a little video about a magnet falling in a copper tube, and we're going to talk about exactly what happened in there. Video kind of tips you off a little bit, but I'd like you to hear a little bit more about it. So let's take a look. We see our copper tube right here depicted, and I want you to imagine that we take a saw and we cut that copper tube along the length like so. So there is our saw in purple, and I'm going to cut along the length of the tube as I would like you to imagine me doing. So let's see that happen. Here we go. I'm sawing the tube right in half, and when I'm done, we'll see what that tube's going to look like having been. And there it is. There's our tube. Having been sawn in half, we can see that here is the body, the tube itself, and all in here, that's the empty part, the hole in the tube. But of course, I've cut vertically from top to bottom, so on the other side, there's a solid part of the tube as well. So that is our tube now, just for us to look at. It's still, I want you to still imagine it a whole tube, but I need us to see it this way. So there's our tube as cut, and we can imagine a tube to just be a bunch of rings stacked one on top of the other. So I'll draw in the rings, and if we have one ring on top of the other when we're done, basically you've got a tube. And now I'm going to take one of those rings and I'm going to shade it in. That'll be the special ring that we concentrate on, but of course all the rings have the same attributes and the same things would happen, but I'll just concentrate on this ring here that I'm shading in yellow. So let's think about that ring for the rest of our discussion, knowing that the rest of the rings all experience the same thing. Okay, I just drew in a magnet right here at the top of our picture. That magnet is falling into the tube. Now in the video they had a sphere, but that sphere was a magnet like any other, and as such, that spherical magnet had north and south pole, just like the magnet that I'm about to draw for us here has a north and a south pole. And I just arbitrarily chose north on top, south on the bottom. Doesn't really matter which way it goes, but that's what we've got. And that magnet, of course, is falling along the length of our tube. It's falling right down like. So to complete my picture, I need to draw some field lines. The field lines go from north to south. And I'll draw 4 loops in here. And of course, put the arrows on to represent the direction of those field lines. By convention, from what we call the North Pole to the South Pole of our magnet. And we remember, of course, the entire premise of this from the video and from our discussion right here is that this magnet is falling. Now, as the magnet is falling, imagine any of the rings, the ring shaded in gold or any of the rings, especially the ones down below. You can ask yourself, what's happening to the amount of flux inside one of these rings, say right here? Well, as the magnet falls, we can imagine more and more denser lines entering the ring as it falls and the flux increases. If the flux increases, we know from Faraday's law of induction that there must be an EMF induced, and that EMF induced will, of course, result in a current, and that current will be directed in such a way that it tries to oppose the change in flux that caused that EMF to happen in the first place. And that, of course, is Lenz's law. Now, we learned last week about a couple different ways we could address this issue and think about what's happening. Lenz's law certainly could work, but I think it's going to be a little complicated for this discussion. So instead, let's imagine, what does it feel like to be this ring? Well, the bar magnet is falling down towards you. But of course, a bar magnet falling towards you is no different than you rising up towards that very same bar magnet. So let's imagine what it feels like for this ring to be rising up towards the bar magnet, which again is exactly the same thing as the bar magnet falling down towards that ring. Charged particles in this part of the ring will feel a force if they are rising relative to this magnetic field. Then that force will have a very particular direction. Take a moment, use a right-hand rule, and figure out what the direction of the force on the positively charged particles in the right portion of the yellow-colored ring, what's the direction of the force on those going to be? Well, I hope you used your first right-hand rule, and when you did, I hope you realized that by pointing your fingers in the direction of the field lines and pointing your thumb upward, again, the ring rising upward is the same thing as the magnet falling downward as far as we're concerned, then your palm would be coming out of the board, and to represent out of the board, I'm going to draw a circle with a dot on the inside. That is the direction of the force that the positively charged particles feel as the magnet falls down towards that particular ring. Okay, now let's think about the other side. We've got this ring, this portion of the ring over here. Once again, we can apply the right-hand rule. Which way should our thumb be pointing if we apply the right-hand rule? Well, I hope you said it should be pointing up for exactly the same reason it should be pointing up over here. Yes, the magnet is going down, but remember, the first right-hand rule speaks to the moving charge in the field, and as far as the charge is concerned, it may as well be rising up, while we may say we believe the magnet to be falling down. If your thumb's pointed up and your fingers are pointed left to right, then which way is your palm facing? Well, of course, you know. Your palm would be facing into the board. So we get a force into the board on the left side, coming out of the board on the right side. And of course, the whole premise of our discussion is that this is a ring that goes into the board here, crosses along through the back of the pipe there, comes out of the board, and then remember that portion of the pipe that in our imagination we cut away? That is going to bring that current right back around. So we get a loop of current that's created. So how can we finish this story off? We were hoping to figure out why that magnet fell so slowly through the tube. Well, if we apply our second right-hand rule, imagine the current flowing out of the board or your screen right here. That means that if we wrap our fingers around this place where the current flows out, with our thumb pointing out of the board, we're going to get a field created by that current that makes a loop around that, of course, and the direction of that field, will be as indicated by our fingers on our right hand, and it will be counterclockwise. Meanwhile, on the other side, point your thumb into the board. Imagine grabbing that with your hand. And you'll note your fingers point clockwise on that side. So now we have to ask ourselves, if we had a magnet that was creating a field directed just like this, directed the way we see it here, inside that ring of copper, what would that magnet have to look like? Well, I'm going to draw it in just a moment. There's the magnet. But of course, we're missing the most important aspect of this magnet, which of course is what's its orientation. Well, what would the orientation be of a magnet that is down here, that is creating a field that's shaped like the black lines up here? Well, that magnet would have a north and south pole. The south pole would be here. The north pole would be there. Now, of course, there is no literal magnet, but the field created by the currents in the wires that are carrying the current because the other magnet is falling create field that's just like a magnet that's oriented like the one I've drawn. And we know like poles attract, opposite poles repel. I said that exactly wrong. Like poles repel, opposite poles attract. And if we look at our diagram, we can see that that there would be repulsion between this imaginary magnet and the actual falling magnet, which explains rather nicely why it falls so slowly in the video. All right, well, I hope that was illuminating, and thanks for watching.